Hello. These slides begin coverage of the material of Chapter 3, in which we begin discussing the microcontroller family that is the primary focus of this course. Let's spend a little bit of time talking about the difference between a microcontroller and a microprocessor. In your PC, the CPU that you have is a high-end microprocessor. A microprocessor requires lots of external support chips, and it's intended to be essentially a multi-chip solution to a problem. A microcontroller, on the other hand, is intended as a single chip solution. Because it's intended as a single chip solution, it's going to have on-chip non-volatile memory for containing the program that's going to run, while a microprocessor does not. It will store its program in external memory. A microcontroller will have far more interface functions on the chip, such as serial interfaces, analog to digital conversion, and other things, than a microprocessor will. A microcontroller also does not have virtual memory. This essentially means that it cannot run an operating system such as Linux or Windows, while a microprocessor does. General purpose microprocessors are typically much higher performance in terms of clock speed, data width, and instruction set than microcontrollers. However, even though I've talked about all these differences, the division between microcontrollers and microprocessors are becoming increasingly blurred. The microcontroller family that we're going to be studying in this class is the microchip pic24 family. This is a 16-bit architecture. It means that most of the registers inside of it are going to be 16 bits wide. The instruction width happens to be 24 bits. The instruction width does not have to be the same size as its general purpose register, and in this case it's not. All microcontrollers have some form of non-volatile memory for storing its on-chip program. This is because when we cycle power, we want it to retain its memory contents. The particular chip that we're going to be discussing in here is going to goes by this very long number. This is actually a member of the pic24H family. There are other families such as the pic24F and others. This number right here indicates is an indication of how much program memory it has. This one supports 32 KI bytes, and this is simply a subfamily designation. All microcontrollers generally have on-chip random access memory for storing variables. This memory is volatile, which means that whenever you turn off power, its contents goes away. This particular chip has 2048 bytes of random access memory. The clock speed on this processor can go up to 80 megahertz. I've already mentioned this is a 16-bit architecture. It contains many registers inside of it, and it has 71 instructions total, which does not include any addressing mode variants. It also has many on-chip modules that we'll talk about as the course progresses. This slide shows a very simplified block diagram of the pic24 core. It's a program counter just like our number sequencing computer did. However, this program counter is very wide, allowing it to access far more instructions than our number sequencing computer. It has an ALU, which an ALU stands for Arithmetic Logic Unit. This does all the computations for the processor. It also has a data memory. This is the volatile memory that I mentioned in the previous page. This is used for storing the data needed for our program. It also has some general purpose registers. We'll talk about what these things do in later slides. The instruction of the pic24 is 24 bits wide. Recall that our number sequencing computer had a 6-bit wide instruction. We're going to view this 24-bit instruction as actually being split into two 16-bit words. Whenever we say word in reference to the pic24, what we really mean is something that's 16 bits wide. The least significant word is shown here. But what about the most significant word? The most significant word we're going to view as having a phantom upper byte of 8 bits. This really is not implemented, but we're going to view it that way. That means that when we take a look at a program counter address, the least significant word is going to store at location 0, while the most significant word of this instruction is going to be stored at location 1. So when we take a look at instructions and we look at the program counter as it fetches words from memory, the program counter is always going to be an even number, and it's always going to increment by 2 each time. So the first instruction will reside at location 0, the next instruction will reside at location 2, the next instruction at location 4, and so forth. This shows the data memory organization for our pic24. Recall that data memory is the volatile memory on the pic24, and it's where we're going to store our variables. This is called a memory map, and it shows how addresses are allocated in this memory space. The first 2048 bytes are actually allocated to special function registers, which we'll talk about in later slides. The next 2048 bytes are actually where we're going to store our variables. This is what we're going to call as random access memory. The first location starts at hex address 800. We can view this memory as either being 8 bits wide or 16 bits wide. If we view it as 16-bit wide, then the very first location for storing a variable starts at location 800. The next one would start at 802. The next one would start at 804. The next one at 806, and so forth. If we're viewing it as being 8 bits wide, it is storing 8-bit wide variable, then our variables will start at location 800, 801, 802, and so forth. Notice that if it's 16-bit wide, each memory location stores 2 bytes, a least significant byte, and a most significant byte. In this class, when we're storing variables, we'll either be using 8-bit, 16-bit, or 32-bit data. Typically, we'll be using 8 and 16-bit data. Why do we need different sizes? Well, we need different sizes depending upon what range we think that variable is going to store. For example, if a variable is only going to store values unsigned range from 0 to 55, then we'd want to use an 8-bit variable. We would not want to use a 16-bit because that would take up an extra byte of data memory, which we don't have that much of. Most of the times we will be using 8 and 16-bit data. Occasionally we will use 32-bit data. The lower 8 bits of a 16-bit value or 32-bit value is known as the least significant byte, while the upper 8 bits of 16 or 32-bit values is known as the most significant byte. So how are 16-bit and 32-bit values stored in memory? This processor stores the bytes of these values in what's called little endian order, which means they're stored in memory from least significant byte to most significant byte in increasing memory locations. Let's take a look at an example. Let's take a 16-bit value that's going to be 8B1A, and we're going to store this at location 1000. So let's look here. Here memory is going to be shown as 8 bits wide, so we have location 1000 storing a byte, location 1001 storing a byte, and so forth. And we want to store this variable at this memory location. We're going to store the least significant byte 1A at 1000. Then we're going to store the next byte 8B at 1001. What about the 32-bit value? Let's store that beginning at location 1002. AC would be stored at 1002. 25 would be stored at 1003. 90 would be stored at 1004, and F1 would be stored at 1005. We can also view this memory as being word-wise. Let's do the same thing. If it's word-wide, then 8B1A would be stored at location 1000. This 32-bit value at 1002, the least significant word, 25AC, would be stored at 1002, while the most significant word, F190, would be stored at 1004. The least significant byte of a 16-bit or 32-bit value must begin at an even address. This is known as word alignment. Let's begin talking about the pic24 instruction set. The first instruction that we're going to talk about is going to be a data transfer instruction. It's going to copy data from a source location and place it in a destination location. We're going to use a terminology that looks like this, in which is going to say copy the contents of this source operand and place it in the destination operand. This operation uses 2 operands, and the method by which an operand address is specified is called the addressing mode. There are really many different addressing modes for the pic24, and we're going to talk about a very limited number of addressing modes in our initial examples. The first instruction we'll look at is called a move instruction that copies the contents of a working register specified here to a destination register specified here. What is a working register? It's a special function register, and there are 16 of them on the PIC24 that range between W0 to W15. Initially, we're only going to use a few of these registers in our examples. Here's an example. We're going to be copying the contents of register W3 to W5. By default, this is going to be a .word instruction. This means that 16 bits of this register are copied to 16 bits of this register. We can also put a .b on the end of this instruction. This means that this is going to be a byte-wide copy instruction in which we're going to copy the least significant byte of W3 into the least significant byte of W5. This copy operation, if we do a byte operation, is going to leave the most significant byte unchanged. The use of the word move is somewhat unfortunate here. A move indicates that we'd be taking the contents of this register and moving it to that contents and somehow deleting the contents of this register. That is not what happens. The contents of the source register is left unchanged by this move operation. A better word would have been copy, but Microchip has used the term move for this data transfer instruction. Let's take a look at an example of this for this move instruction. By the way, these addressing mode is called register direct because we're directly specifying registers as our two operands. So let's execute a move of W2 to W1. Notice that I have not specified .b here, so it's going to be a word mode operation. This shows the before register contents, and this shows the after register contents. So here we're going to take the contents of W2, which happens to be 64DE, and move them in, and copy them into W1. So after instruction execution, W1 is going to contain the 64DE. Let's change this to a byte operation. So in this case, it's going to copy the least significant byte of W2, which is DE, into the least significant byte of W1. So after the operation, W1 is now going to contain an 8B DE. So we've seen how to copy values between working registers. What about copying a value from a working register to a data memory location? This instruction will do that. This will copy a value in a working register to a data memory location. This particular example will copy the 16-bit value in W3 to location 1000. The form of this particular instruction only supports word operations. It's illegal to put a .byte here. By the way, Microchip refers to locations in data memory as file registers. We say that the source operand uses register direct addressing, while the destination operand uses file register addressing. Let's take a look at an example. Let's assume that W3 contains the value 64DE, and that we want to execute this instruction that copies W3 to location 1002. Before instruction execution, 1002 contains this value 25AC. Once this instruction is executed, this value right here is copied into this memory location, so 1002 will now contain 64DE. The previous instruction moved a value in a working register to memory. Let's go the other direction. Let's move a value from data memory to a working register. So here's an example of this instruction form. Move the contents of location 1000 to working register W3. Just like the previous form, this instruction form only supports a word operation. Let's look at an example. We want to copy the contents of location 1002 to working register W3. Before execution of this instruction, W3 contains a 64DE, while location 1002 contains 25AC. After instruction execution, the contents of 1002 25AC is copied into working register W3. Notice that the memory location 1002 contents is left unaffected while W3 is modified. This slide shows the machine code format for the move working register to data memory instruction. Up to this point, we have not talked about the machine code formats formats, and we're not going to emphasize machine code formats for the pic24 in this class. We'll do this one example and then move on. This right here, BB23, that means that this is bit 23 of the instruction word. It's the most significant bit of the instruction word. This means that this is bit 0 of the instruction word, the least significant bit. Recall that the instruction format is actually 24 bits. So in looking at this, we see that these upper 5 bits of this instruction is fixed at 10001. The remaining bits here, these FF bits, are used to specify the file register location, the data memory location, while this 4-bit value right here is going to specify the working register number. By the way, these F values here are the upper 15 bits of the 16-bit address. The reason for this is that since it's a word operation, we know that we're going to be always copying to an even location, which means that the lower bit will always be a 0. So we only need the upper 15 bits of the data memory location. So let's do a numerical example. We're going to move W3 to location 1002. So these lower 4 bits right here, which corresponds to these, are going to specify W3, so it's going to be a 0011. These upper 5 bits here are fixed, so that's these bits right here. Location 1002, if we break that out in the binary, this 2 right here is going to be these 4 bits. The 01 is going to be here, and the middle bits are all 0. And what we're going to do is going to take the upper 15 bits of these, and that's going to become these F bits right here. If we convert this to hex, we get this machine code 24-bit value of 888013. So you've seen how to move words between working registers and data memory, but what about a byte? Well, we can use this particular instruction for that purpose. This instruction is read as move working register to file register. WREG is a keyword in this instruction, and it stands for register W0. This instruction actually provides upward compatibility with an earlier PIC microcontroller. It was an 8-bit microcontroller. There are 2 limitations on this instruction. One, you can only use the WREG keyword here, which stands for W0, and 2, the file register location must be within the first 8,192 bytes of data memory. It can either be a word or a byte operation. So here I could move the 16-bit value and W0 here using the keyword WREG to location 1000, or I could move the byte value in W0 to location 1001. If I do as a word operation, it must be to an even location in data memory. Bytes can either go to even or odd locations. Here's an example of a byte version of this instruction. We're going to do move.byte working register to location 1001. Working register, which is W0, contains E34F. Memory contents location 1000 contains 8B1A. Recall that when we view multi-byte values in memory, that location 1000 is going to contain the least significant byte. So this actually, if I view this as 8-bit wide, is going to contain 1A, while location 1001 could contain the most significant byte, so it will contain an 8B. After we execute this instruction, this value right here, 4F, is going to be copied to location 1001, which is going to be the most significant byte of this address. So this 8B here is going to now become a 4F. So going the other direction, we can move either a byte or word from a file register location to the working register, which is W0. F can only be, as mentioned previously, in this form of the instruction, the first 8,192 bytes of memory. There's also another form of this instruction in which we're going to leave off WREG and just specify the file register location. If we do this, this copies the memory contents from itself onto the top of itself, which means that the memory contents is unchanged. While this would seem to be a fairly useless instruction at this time, we will find there's indeed a use for this instruction, and we'll talk about that in another lecture. This shows the machine code format for the move value from file register to working register. We're showing this to illustrate a point. The reason for the limitation that this can only be in the first 8,192 bytes of data memory is because in this machine word there's only room for 13 bits to specify the address. This gives us a range if I write this from 000 to 0x1FFF. That's the range that these 13 bits of address can support, and so that's why this particular instruction and the other version of it, which moves from working register to file register, only supports an address in the first 8,192 bytes of program memory. There's a bit in here, there's B here, that's going to allow us to specify either a byte operation or a word operation. Here's an example of this instruction operation. We're going to move a byte from location 1001 to the working register, which is going to be W0. Before we get started, W0 is going to have a 64 DE. So taking a look at this memory, this value 1A is actually going to be stored in 1000. 1001 is going to contain this byte right here, 8B, and we execute this instruction. The 8B is going to be copied into the lower byte of W0, least significant byte of W0, which will replace this DE with an 8B. The upper byte, 64, will remain unchanged. Let's talk about the concept of a literal. A move instruction involving a literal allows us to initialize a working register with either a 16-bit constant or an 8-bit constant. We indicate that an operand is a literal by using a pound sign in front of it. So this instruction says move the constant value 1000 into W2. This instruction right here says move the constant value 8B into W3. Since this is a byte operation, only the least significant byte of W3 would be affected. Notice that this instruction right here is very different from the instruction that says move 1000 to W2. This would say take the contents of this memory location and move it into W2, while this instruction right here says take the immediate value or the constant value 1000 and place that into W2. This particular addressing mode right here is called the immediate addressing mode. Here's an example that illustrates the difference between immediate addressing and file register addressing. This instruction is going to use immediate addressing. Here's the pound in front of this constant, and this is going to say move the constant value, the literal value 1000 into W2. So after execution, W2 would contain the value 1000. Here this is saying move the contents of location 1000 to W2. This is file register addressing. In order to know what happens here, we have to look at the contents of location 1000. It contains an 8B1A, and this value is going to be copied into W2 by this instruction. Notice that W2 does not get the value 1000. Here's a byte version of this instruction. We're going to move the constant value, the immediate value F2 into W2. After we execute this instruction, the lower byte of W2, which was a 38, is now going to be changed to an F2, and the most significant byte is going to be unchanged. Notice it doesn't make any sense to have an immediate operand as a destination. For example, move W2 to the immediate constant 1000. That is illegal and is meaningless. Finally, we're going to wrap up our coverage of the move instruction and various addressing modes by talking about an addressing mode known as indirect addressing. And we're going to talk about a simple form of this indirect addressing called register indirect. We indicate register indirect by putting brackets around a working register. When we do this, what we're saying is that we're not copying the contents of this working register, but instead we're treating the contents of this working register as an effective address, as of the operand, and we're going to go to that location, take the contents of that, and then that will be our actual operand. I realize that that's confusing, so it's best to actually take a look at an example. First, let's just review register direct addressing. Here we're simply copying the contents of W0 to W1. So if W0 contains location or contains the value 1000, then after we execute this instruction, it's good that value 1000 is going to be copied to W1, and W1 will contain the value 1000. Now let's put brackets around these two operands and see what happens. So bracket says, okay, treat W0 as an address. So we're going to take a look at W0 and we'll say, okay, this contains an address, and that address is going to be the value 1000. So what we're going to do is we're going to say, all right, let's take the contents of 1000 and let's copy it somewhere. Where are we copying it? Well, we're copying it to the indirect W1 register. So what does that mean? Well, we're going to take a look at W1. It contains the value 1002, and because this has brackets around it, it says we're going to treat that as the address, the destination address. So we're going to copy the contents of 1000 to the destination 1002. So when we do a copy, the contents of location 1000, 8BFA, is going to copy to the destination 1002. And so after we do that, this location is going to be changed to the value 8BFA. We could leave brackets off the source operator for or the destination. If we leave brackets off the source, what this is going to say is this is going to use register direct addressing. So it's going to say, all right, take the value that's in W0. What's the value in W0? It happens to be 1000. So take that value 1000. And let's copy it somewhere. Where are we copying it? Well, this is register indirect. So it says, all right, W1, treat that as an address. The address is 1002. We're going to copy the contents of W0 to 1002. So after execution of the instruction, the location 1002 is going to be changed to 1000. You may be asking yourself, why do we even need indirect addressing? The answer is that with indirect addressing, we can do a memory-to-memory copy with only one instruction. You may be tempted to write something like this: move the contents of memory location 1000 to the destination 1002. However, this is illegal. There is no form of the move instruction that supports this. Instead, without indirect addressing, we have to do something like this: move the constant location 1000 to W0, then move W0 to the destination location 1002. However, we can do it with one instruction if W0 and W1 have the values 1000 and 1002 in them. We'll discover later there are actually 6 different forms of indirect addressing. We'll cover more of the indirect addressing modes in Chapter 5 when we talk about pointers in the C language. At this time, we only want you to understand the simplest form of indirect addressing, which is register indirect, as shown in the previous slides. This concludes our introduction to the pic24 architecture, instruction set, and addressing mode coverage. We'll cover more instructions starting in the next lecture. Problems 16 through 32 all use table 3.6, which gives some initial values for working registers and also memory locations. These values are the same at the beginning of each problem. So let's start with problem 17, which says move that byte, the contents of location 1001 to WREG. So WREG is the destination, which means that W0 is going to be modified and this least significant byte is going to be changed. But what it's going to be changed to? Well, let's figure out where 1001 is. This memory is shown as being 16 bits wide. So this first byte right here, least significant byte, is going to be sitting in 1000, while this most significant byte there is going to be sitting in location 1001. So what we're doing is removing this byte right here, 38, to the least significant byte of W0. So the final value of W0 is going to be 0x1038. So problem 19 says move that byte, register indirect W3 to register indirect W4. Let's remember what register indirect means. It says to treat W3 as containing an address. So it's saying take the byte stored at this address, which is going to be 0x1000. Take that byte, and we're going to move that to where? We're moving it to W4, register indirect. Register indirect says, okay, look inside W4, treat that as an address. So we're actually moving that to memory location 1005. So let's go ahead and figure out what these values are. Let's find the byte stored at location 1000. Well, taking a look at location 1000, we see that the byte stored at location 1000 is 2A. So this is going to say take 2A, and we need to write that to 1005. Well, where's 1005? Well, 1004 is going to be this byte. This byte right here is actually 1005. So this memory location is going to change to this 2A is going to replace this 4D. So that's going to be 2A there. That 19 is going to remain unchanged. So memory location 1004 is a 16-bit value is now going to contain 2A19.